Thank you. So I just submitted my thesis, so I'm technically still a PhD student here at Simula, supervised by, amongst other, Kent and Maria. So thank you for the invitation to come here and talk. So yesterday we heard two talks about infusion and also about compartment modeling or resistance modeling of flow through the brain. So I will try to, in some sense, tie these talks together today. I will talk about ICP during the infusion test and try to tie that to flow into the brain. So we heard many times, I would say, this in these talks about the CSF flow and where it comes from, where it's absorbed. But it's probably safe to say that at least CSF flows from the choroid plexus and some portion of it is taken up by the granulations, but we can't know for sure how much exactly that is accounting for. So there are probably some other pathways and absorption routes, maybe some other production sites that we're not completely sure of the importance of. Okay, we know that CSF at least may enter these paravascular spaces, so that's what I'm going to call paravascular spaces. But it's not clear whether it's like an absorption or it goes through the brain, whether it goes through the brain and out, back into the subarachnoid space, or if it's absorbed within the brain. That's not clear. In addition, we have capillaries, and it was an interesting discussion this morning. We also think that the capillaries has such a huge surface area, so about 10 meters or something like that. So it has a huge potential for some water filtration, at least, over the capillary wall. And also we heard that cardiac and respiratory effects is moving CSF, at least in the subarachnoid space, and thus it may also affect flow into and within the brain as well. Okay, so it has been a lot of talk about respiratory effects, at least yesterday. We had a lot of talks that were looking into these respiratory effects on CSF movement. And I'm quite happy about that, because I was also supposed to address this point from a very different angle. So we just got the paper accepted on this matter. So a lot of people have used MRI to address this question. And we had a talk yesterday about the powers, but also the limitations between the limitations of MRI to address this question. So we have actually had pressure measurements inside the brain instead of measuring with MRI. So what we did is first we had the intracranial pressure measurement in two locations at the same time. So from this you can get a pressure gradient, right? Just compute the difference between these two. And we have data over 15 hours approximately for each patient. And we have 10 or 9 patients that we could use the data from. So we have a lot of data, 15 hours in 9 patients. So we would need to simplify all this a little bit. So we did that by doing a Fourier analysis to look at the most important frequencies. And we found that in the pressure difference, we had the cardiac frequency that was important, and we had the respiration frequency that was also quite important, but in the pressure difference, it was much smaller. So based on these pressure measurements, we made a simplified intracranial pressure gradient for each patient that was only consisting of one cardiac and one respiratory component. And with these data as input to a fluid dynamics model solving Navier-Stokes equation, we could calculate flow, in this case in the aqueduct. So we could see the effect of cardiac versus respiratory respiration effects. And then we can, of course, after simulation, we could post-process and see the effect. And it's not going to be a one-to-one relationship between the input importance of cardiac and respiration versus the output importance of cardiac versus respiration. So as we can see here, for instance, if you have a pressure gradient going like this, so this is everything here has to do with the Womersley number, right? So if you have a pressure gradient going like this, so this is obviously dominated by cardiac pulsations, but you have respiratory contribution here as well. But in the corresponding flow, in the aqueduct, it's more prominent that the respiration plays an important role. So overall patients, we had about 3-fold dominance in the cardiac pressure difference. So it was about 3 times larger. So the cardiac pulse was about 3 times larger than the respiratory pulse in the pressure. But for the flow, these amplitudes for the cardiac and respiration, they were approximately the same. So even though you have a 3 times larger pulsation in the cardiac ICP difference, you would have the same amplitude in flow in cardiac and respiratory effects. And just to compare these numbers, these gradients with what would be expected if we took the third circulation as the truth. So in the third circulation, like when you have production in the choroid plexus, and it flows aqueduct up to the granulation, and you produce about half a liter a day in the choroid plexus, that would require only like 100 of these other gradients. So these pulsatile gradients are definitely larger than the static gradient associated with the third circulation. So we can just show you how we obtain this data. So this is one of the patients in the aqueduct. You can see it. I'm going to zoom in a little bit. Not sure if you can see it here, but so this is pretty similar. This is the simulation with input data as these pressure measurements. Yeah. So another point is that the volume, right? I said that these amplitudes, so here the green, this is decomposed flow rate. So the green one is the respiratory component, blue one is cardiac component. So although these amplitudes, the green amplitude, the blue amplitude, although they are the same, the volume, if you integrate here, right, over one cycle, will be much larger for respiration because the period is so much longer, so it allows for time to move more fluid. Okay, so we see that longer waves obviously can move more fluid in one direction, has more volume associated with it. So in light of the test, obviously, we can look at this infusion test where you measure the pressure inside the like that. When you inject the fluid, obviously you increase the pressure like this. So you may look at this as like a gradual increase in ICP over a long period of time. So this takes approximately 20 minutes or so. So it can be looked at this long wave of increasing ICP. So obviously this will or has the potential to move fluid around in the brain. And this is what they do, right, when they do experiments in the glymphatic system to address whether the fluid goes into these arterial spaces. They inject fluid into the subarachnoid space very often. And in some of these studies, the pressure has been rise as up as to 2.5 millimeters of mercury. So we were thinking of modeling this in a study to model the link between these infusion rates. So we're going to use a model that is based on models with experimental infusion tests, and see how it affects flow also into paravascular spaces. So this has not yet been published, but we're going to see if we can, I'm not sure how deep into the rabbit hole of osmosis we're going to dig, but that's at least Anders and Karen's wish. But for now, we haven't much into that. So this is more hydrostatic pressures, similar to what Keith presented yesterday. So we build this resistant resistor model. So we have inflow into the subarachnoid space here, and from the subarachnoid space, we flow into paravascular spaces. It can have some filtrations with the capillaries, and we can also, from the paravascular spaces, we can have flow continue into these PL sleeves. So this is an assumption, because yesterday we talked about this circular flow in the glymphatic system. So that's virtually impossible to model when you use hydrostatic forces. You cannot have this circular flow. So we assume that it can have some other exit pathway, possibly around some PL sleeves, around the veins going out the lymphatic system. But we also made several modifications of this model that does not include this, but rather like a circular going back to the subarachnoid space. And we'll not present too much of that today. But we also have the ability that it could go right through the cribriform plate, from the subarachnoid space right through the cribriform plate and into the lymph system. And obviously, as Anders presented yesterday, this part is the where you can go through the arachnoid granulation in the dural sinuses. So we keep this part. So the interesting thing here in our study was to try to quantify how much will go into the area here, how much will go to the cribriform plate here, how much will go through the dural sinus here, and maybe most importantly, will that change during an infusion test? So when you add more fluid here, would that change the distribution from where these outflow pathways, the CSF, where CSF flows as an outflow pathway? So we created this compartment model. So this is a quite simple compartment model consisting of only two pressures. So we have the ICP in the subarachnoid space and in the paravascular space. So we have one equation for the subarachnoid space, let's say, and one for the paravascular space. So all these terms, as was addressed yesterday, is describing flow from one compartment to the other. And that flow is driven by the pressure difference between these two compartments. So for instance, here we have the change in subarachnoid space pressure that would be affected by the inflow rate, or inflow rate and production. And also here the pressure difference between the dural sinus and the pressure in the subarachnoid space. So this term here would be the flow from the subarachnoid space into the dural sinuses. And this is the corresponding flow rates for all the different compartments. And also this term here is quite interesting, because this will be the flow from the subarachnoid space into the paravascular spaces. So we can also quantify that. But obviously we have a lot of parameters here, right? We have these resistances, and some of these has been calculated already, for instance, by Keith. So we used some of the values from the paper by Keith Sharp and Fagui. So you saw this model yesterday, right? But the problem here was that it does not allow for any flow further into the brain. So the resistance was calculated down through to the pre-capillaries, and then it was truncated, and then it was calculated after that on the post-capillaries and out on the venous side. So we also wanted to try to compute the resistance through the rest of the system, either through capillary gaps around capillaries or through the extracellular space. So for the capillary gaps, we used this network model by Payne and Nelbouri. And similar to what was done in the paper by Fagui and Sharp, we assumed these donut shaped around. So obviously it's not perfectly correct, but it's a good approximation, first approximation. So we added up trees like this, and and assumed that it was approximately 1.5 billion capillaries in the brain. So we used this tree as a model for that. So we tied together this model by Vegard and Sharp and put on the end of that one this model by Payne and El-Bouri. And in addition, using the hydraulic resistance of the capillary wall and the huge surface area of the capillaries, we could calculate the resistance over the capillary wall. So we found that to be 125 millimeter mercury per milliliter per minute. So compared to the total resistance, it's about 10 times larger than the total resistance you see in patients, the total resistance to outflow. So this it's a quite resistant membrane compared to the total resistance you see in patients. And from Karl-Erik Holter's paper, calculating the permeability in tissue, we were able to also measure the resistance in the tissue going from an artery to a vein, and that was calculated to be around 80. So it's slightly easier, it seems, to move through the extracellular space than to move out and in of the capillaries, at least in our calculations. And finally, through the capillary gaps, that was 100 nanometers extra space around capillaries for fluid to move in, we calculated this resistance to be even lower, so about 32 millimeters mercury per milliliter per minute. So obviously this is not going to be proportional to the flow, because you also have a pressure on the other side driving this flow, right? So you need a resistance and you need a pressure gradient to drive the flow. So these resistances here, they're put onto the model in these places. And this one has been calculated by Vegard and Sharp, this one as well. And this one we found in experimental studies. But these were, okay, so it was done in a sheep and so on, but this is the best we can do for now. And we set these output pressures as well. This is, of course, just an average in the capillaries. And we assumed here also 8.8 in the PL sleeves, the same as in the dural sinus. For the cribriform plate, we assumed that on the other side it was equal to the lymph pressure that was calculated or measured by Silver to be around 2 millimeters of mercury. Okay, so when we put this into the model and we compare it to the reference model, which is the clinically used model, having a total resistance that was a little bit higher, we get that in the normal reference models, you get up to a pressure of about 24 millimeters of mercury. In our models, with all the assumptions we made, we get it up to about 21, and that is still within the range what's considered normal in healthy patients. And we can here see that we can also compute the pressure difference between the CSF in the subarachnoid space and in the perivascular space. So we get two curves, one for each. So that means we can actually compute the flow from the CSF in the subarachnoid space into the perivascular spaces. And this is a little bit messy, but here is all the outflow pathways. So crib is the cribriform plate, and you see here is before infusion, here we do the infusion, and here is after infusion. So here's the cribriform plate, arachnoid granulations in orange, perivascular space, capillaries, and then here is the venous or the PL sleeves on the venous side. So we can see here that the PVS seems to actually be turned on after the infusion. For instance, you can see that the cribriform plate has higher flow before the infusion, while at the infusion the perivascular spaces are more important. To sum up this, you can see, so this is like a diagram showing the most important part before the infusion test. So there's almost no flow between the subarachnoid space and the perivascular space. So this arrow actually points in this direction. So before the infusion, we had almost no flow, but if there was any flow, it was from the perivascular space to the subarachnoid space. So this is due to the assumption that we have some filtration here by the capillaries. So, I mean, if we took away this assumption, you would have very little flow, but it will go from the subarachnoid space to the perivascular space. So the flow that comes in, 60% left through the granulation, 40% through the cribriform plate. But during the infusion at the plateau level, obviously the infusion rate plus the production is obviously larger. And the granulations increase by a factor of, right? It's a factor 5 or even 5.5. While the cribriform plate only increased by a factor 2. But what's more important here is maybe that flow into perivascular spaces is increased a lot. And it even reversed direction in this case. You can see that the capillary filtration is also altered. And obviously the outflow is altered from this perivascular space through the brain. So based on these volumetric flow rates and estimates on the area of the perivascular spaces, we estimated that this was about 2 micrometers per second. So that's quite small. So this is a quite small estimate compared to what, for instance, Douglas reported in his talk. So it was reported about 20, right? But we only estimate that it's around 2 micrometers per second based on these calculations. I mean, obviously we use these round circular donuts and not these elliptical geometries, would maybe increase this estimate by a factor 2 or 3 or something like that. And for the next steps, I mean, how deep are we going to deep into this? Starling forces and osmotic gradients. I think we need to get more of an overview before we decide on this. So I was happy to hear your talk this morning. In addition, we have the resistance parameters that we calculated. Obviously, it's hard to get good experimental values from human beings. So sometimes we just have to pick from different species. But that's how it is at the moment. And we didn't include this arterial and the respiratory pulsations. But in these types of model with hydrostatic pressure gradients driving the flow, it would just be a back and forth flow, right? It wouldn't be any mixing with these simple type of models. So that's, we also had no spatial dependency. It's just a simple compartment model. And this capillary pressure is maybe also a bit like an itch on this model. We don't know exactly how to set it, and we have to set it like at a constant level, at least for now. Okay, that's it for me, and I would like to thank at least Karen, Marie, Anders, and Kent, who are all here. And thank you for your attention.
Thank you very much, Vinje. It is on, sorry. All right, so you used the word simple many times. For some of us, it's not that simple. So this might be a very naive question. So when you envision the fluid, so the water, not the marker, going down the perivascular spaces, whatever you like to call it these days, I would kind of have thought that it would be quite easy for the water to go in between the astrocytic end feet, where there is a gap. And that's where you find the 80 millimeters mercury resistance, which is not that different from getting actually across the capillary where there'll be a real barrier. You actually have a membrane barrier. So is it really that difficult getting, if you were a water molecule, between the astrocytic end feet, which have gaps of like 30 nanometers at least or something? Or?
So this even, we didn't even include the resistance over this end feet. This resistance in the extracellular space is only in the tissue itself.
Okay, so it's actually that difficult for a water molecule to move between cells.
But that's a bit controversial. I mean, this is based on a piece of tissue in a mouse. And we did calculations. It's a paper from 2017. claiming that this resistance is quite high and higher than what has been reported earlier. But that's it's only in the tissue itself and not including these unfit barriers or clefts.
Yeah, all right, thank you.
Okay, thank you. It's amazing for me to see that using ICP monitoring at in two compartments, you can get so nice information that in fact represent the gradient, if I well understood the presentation. Mm-hmm. So my question is, did you apply some filter on the first signal measured? And if this filter is high level frequency, you remove the high frequency, didn't you think that applying this kind of filter in your signal may affect more the cardiac information than the breathing information?
That's a good question, and I actually have some slides to show you here, right? So this is what we see typically over 6 minutes or something in the pressure difference. Okay, so the pressure difference is quite small here. This is oscillating flow, but you cannot really see but it goes up and down a little bit. That is not related to cardiac nor respiratory effects, right? And then you get this signal. So this is not filtered. This is just the signal itself. And we apply the filter to this Fourier transform with the cutoff frequency of so cutting off higher frequencies, which was way up in the Fourier frequency spectrum, right? So I'm not sure if that will affect this bump more than this bump here. So we've seen this on both the unfiltered and on the filtered data, that the cardiac is higher, but exactly how many % that would change the result, I'm not sure, but I don't think it will affect it too much.
Well, first, it's just wonderful to see finally the whole system put together, and it's a really good start. My question is, have you had a chance to do some parametric sensitivity to find out which parameters are the important ones in determining, say, whether flow changes in the perivascular space?
Yeah, so we did actually in this paper that we have written up now, but haven't submitted yet. We explored like 7 or 8 different type of models, changing the parameters we thought were most important. And so I have a table here actually showing all the changes in parameters and all the resulting flow rates. So I'm not asking you to look at this right now, but for instance, if you have an infinite resistance here in model number 9, infinite resistance over the capillary wall, so no filtration there, then you will have, of course, you will have an inflow from the subarachnoid space into the perivascular space, and that will not reverse at any time, right? So we have done this parameter study, looking at different parameters and their importance. And obviously the radius of these gaps is quite important.
Thank you very much for presenting. You mentioned for the lumped parameter model that you also tried the variation with the full circulation as in the lymphatics, but that didn't make any sense. Is that correct?
Well, you could say the only possibility there, if you have like a circulation model, it wouldn't really be a circulation model. It will just be some capillary filtration going in 2 directions to the subarachnoid space, right? So you cannot get it to be a circle, but you could get it to be like a fountain from the capillaries and out, or from the subarachnoid space into the capillaries. So that's basically, it's this model 8 here. So that means you had, before the infusion, you had the 10, you have some capillary filtration going out into the subarachnoid space, but during the infusion, you actually had no flow in the perivascular spaces at all.
Okay.
So it's not really a circular model, it's more like either out or in.
Okay, so what I find confusing then is why you still call it glymphatic.
Yeah, so then it's not really glymphatic, so to say, because it's not circular. But I mean, it could be modified to, at least there's some communication in between there.
I just think the terminology is very important because the definition of the glymphatic as it was introduced requires that circulation, plus requires the aquaporin fours as the main channels and that are transporting it. So by sticking to the name glymphatic, we are making things less clear than they need to be.
Okay, thanks. Yeah.
Okay, final question.
So it makes complete sense that if you increase the pressure in the subarachnoid space outside of the perivascular spaces that you're going to increase flow into there. So that makes perfect sense. I'm interested in whether you found a point at which, did you explore the amplitude of the infusion and what was the point at which that flow started to change relative to the resistance for the capillary outflow?
We haven't checked different levels of infusion yet, so I can't answer that question, but it would be quite simple to just check that, yeah.
I guess I'm thinking of the other data that suggested that there was a sort of a point at which that made a difference or didn't make a difference with injections into the, at least from Roxana's data.
Okay, yeah, I see.